Hi, this is Jaxal. Do we have a connection? Do we have a connection? Do we have a connection? Hello? 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 Checking. Do we have a connection? 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 Connection. 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 I wonder if I should speak fast in short sentences. 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 Should I go 2 minutes or so? 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 Testing, testing. Wishing everybody a good day. Testing, testing. Wishing everybody a good day. Testing, testing. Wishing everybody a good day. Testing, testing. Hoping everybody remember to bring their umbrellas. 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 Testing, 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 testing. From the UFT campus, Jaxal here. From the UFT trying to connect with AISC. Jaxal here. From the UFT trying to connect with AISC. Jaxal here. From the UFT trying to connect with AISC. Jaxal here. Trying to connect with AISC. This is Jaxal. Hi, this is Jaxal. I'm going to be presenting paper by Shungya Xing. Hope I'm not butchering his name. And the paper's title is Temporal Pattern Attention for Multivariate Time Series forecasting. And basically, what they're trying to do is
This is
to
Yaxal. I'm going to be presenting a
um,
paper by Shungyao Xing. Hope I'm not
propose
butchering the name.
a
And the
way
paper's title
of
is Temporal
analyzing
Pattern
multivariate
Attention to
time series.
Multivariate Time
And instead
Series
of using the normal recurrent
Forecasting.
neural networks,
And
they're proposing
basically,
a thing called
what they're trying
convolutional
to do
neural
is
networks.
to
And
Yaxal. I'm going to be
basically,
presenting
switching
paper by
from a temporal
Shungyao
analysis
Xing.
where you
Propose
usually have um,
and the
a
paper
selection of time
analyzing
steps
multivariate
where
time
you only
series.
recall or
And
take
instead
into
of
account
using the
the
normal
previous
recurrent neural networks,
couple of
they're
steps
proposing
into
basically a thing called
trying to do the analysis as if
convolutional
you were switching
neural
from
networks. And
a
basically,
frequency domain.
switching from a temporal
And they do
analysis
this
where
by
you usually
basically
have
putting
a selection of
weights
time
and
steps where you only recall or
and
take into account the previous
so
couple of steps
what they're saying is
into trying to do
um
the analysis as if you
they
were
they're calling
switching
these
from
weights
a
attention
frequency
concept.
domain.
So it's basically
And they
having
do this by basically putting
the testing instead of it in a
weights
temporal way, they're starting to do
and
the relations
where you only recall or
between
take into
the time
account the
series
previous
because it's like
so what
multiple of
they
them that
what
sometimes
they're
can
saying
have
is
uh,
trying to do the
periodic or not
analysis
periodic
as if they're calling these
interdependencies.
weights
Um, okay,
attention concept. So it's
so what
basically
they claim is
having
that by introducing
basically
this
putting
attention concept,
the testing instead of doing it in a temporal way, they're starting to do the relations between the time series because it's like
they're
multiple
the
of them that
ones
sometimes
this
can have
time
periodic
steps
or not
between them
periodic
as
interdependencies.
in the
Okay.
frequency domain, they
So
would
what
be
they
the ones
claim
that have
is
like
that by
recurrences.
introducing this
Um,
attention concept,
and so
instead of
they
doing it in a temporal way, they're starting to do the
claim
relations
that they can use
between
they can
the
it can be
time
used
series because it's
for
like multiple of
periodic,
them that sometimes can have
partial linear, non-periodic, and non-linear tasks, and that
kind of like dependencies.
this
Like
method
in
is
the
more
frequency
effective,
domain, they would be the
particularly
ones that
when
have
you're
like
training it in the learning
by
process,
introducing
because the
this
performance in terms of precision,
and so
recall,
they
and FY score
claim that
much better than the
it can be used for
recurrent neural
periodic,
networks. Um,
partial linear, non-periodic,
so
and
they also claim
non-linear
that
tasks.
it's possible
And
to
that
capture not only short-term
this
temporal
method is
patterns,
more
but also
effective,
long-term
and
temporal
particularly
patterns.
when you're doing it in the learning
Um,
process,
yeah,
because
and
the
they just do
performance
it
in
by
terms of
creating
precision, recall, and FY
they call
score,
it CNN filters, which is convolutional neural network filters.
it's it can be used for
Recurrent neural
periodic,
networks. So one of
partial linear, non-periodic, and
the things that
non-linear.
they're basing some
It's
of the
possible to
assumptions
capture
is that
not only
the
short-term temporal
um,
patterns, but also long-term temporal patterns.
the time series
Yeah, and
in a
they
way
do this by creating
has like a pattern in the
FY
in the
they call it
temporal
CNN filters, which
uh,
is convolutional neural
domain,
network
so that when
filters.
you go into the frequency domain, then it's kind of like
Recurrent neural networks.
um,
So
equally
one of
spaced.
the
Um,
things that they're basing some
and
of the
then the other
assumptions
thing is
is
that
that the
because they're using multivariate time series, or many of them, to
the time
analyze them,
series
they kind
in
of
a way has
I'm gonna call cluster them. So they put them together in the frequency
a
domain. So
pattern
they
in
take
the temp
the frequency components of every
domain
time series
so that when
and
you
this
go into the frequency domain,
weight,
then it's kind
and
of
then
like
they sum them based on a
equally
specific
spaced.
formula,
One of
and so they do the
and then the other
analysis
thing is
in the
that
whole frequency,
because they're using
the
multivariate
sum of the
time series,
frequencies
so many of
instead of
them,
individual
to
frequencies.
analyze them,
And
they kind of has I'm gonna
this
call
can be seen
cluster
as
them, so they put them
when you have
together in the
many
frequency
waves with
domain. So
different
they take the frequency components of every
um, so when, for example, you're analyzing
time
waves of
series
different
in
colors or
this
sounds, for example, of different
weight, and then they they sum them based on
different sounds, then
specific
what
formula,
you do is you take the
and
sum of the frequencies
so
and you
they do
kind
the
of
analysis in the
envelop them
whole
together so that when you analyze them, you
frequency,
see the,
the sum of
the
the
total
frequencies instead of
differences
individual
um,
frequencies.
of the
And
bulk. So it's kind of like a
it can be
wrapping.
seen as
So you see
like you have
the
many
way that
waves of
the wrapping
different
behaves instead of the individual frequencies. So this is
and
what they're doing
so
in
when,
this
for
case.
example, you're analyzing waves of different colors or sounds, for example, of different weight, and then they sum them based on
Different sounds, then
specific
what
formula,
you do is you take the
and
sum of the frequencies
so
and you
they do
kind
the
of
analysis in the
envelop them
whole
together so that when you analyze them, you
frequency,
see the,
the sum of
the
the
total
frequencies instead of
differences
individual
um,
frequencies.
of the
And
bulk. So it's kind of like a
it can be
wrapping.
seen as
So you see
like you have
the
many
way that
waves of
the wrapping
different
behaves instead of the individual frequencies. So this is
and
what they're doing
so
in
when,
this
for
case.
example, you're analyzing waves of different colors or sounds, for example, of different weight, and then they sum them based on
Different sounds, then
specific
what
formula,
you do is you take the
and
sum of the frequencies
so
and you
they do
kind
the
of
analysis in the
envelop them
whole
together so that when you analyze them, you see the,
the sum of
the
the
total
frequencies instead of
differences
individual
um,
frequencies.
of the
And
bulk. So it's kind of like a
it can be
wrapping.
seen as
So you see
like you have
the
many
way that
waves of
the wrapping
different
behaves instead of the individual frequencies. So this is
and
what they're doing
so
in
when,
this
for
case.
example, you're analyzing waves of different colors or sounds, for example, of different weight, and then
Okay,
they
how's the audio here?
Different sounds, then what you do is you take the sum of the frequencies
so
and you
they do
kind
the
of
analysis in the
envelop them
whole
together so that when you analyze them, you see the, the total differences um,
What's going on?
so it's kind of like a wrapping. So you see the way that the wrapping behaves instead of the individual frequencies. So this is what they're doing in this case.
Okay,
Okay, how's the
um,
audio here?
okay. Can people hear me fine? Any feedback or anything like that? Oops, what's that? Okay, all right then. So uh, I'll give you the short and sweet for understanding deep learning requires rethinking generalization. And this can be even shorter than 5 minutes, but maybe I can fill that up too if people want. Uh, the quick answer here is, I mean, the summary of their central finding is deep neural networks easily fit random labels. So they
Okay,
wanted to
okay.
test out to
How's the
see
audio
how
here?
well a lot of
Okay.
this learning
Can
theory
people hear me fine?
works.
Any feedback or
And
anything like
what
that?
they did is they started abusing the data and seeing
Oops,
how
what's that?
well
Okay.
a suite of standard neural
All
networks
right then.
performed
So
and
uh,
what happens to
I'll
the
give you the short
generalization
and
error.
sweet for understanding deep
And
learning
what they
requires
found is that
rethinking
for
generalization.
training,
And
um,
I
pretty
this
well,
can be
all the
even
standard
shorter
neural
than
networks
5 minutes, but
train
maybe I can
beautifully
fill that up
well,
too if people want.
no matter how much they
Uh,
abuse the data. So, I mean, the first thing
the
they did is
quick
they
answer
randomized
here
all the
is,
labels.
I mean,
This
the
is on
summary of
CFAR10
their
and
central
ImageNet,
finding is deep
and
neural networks easily fit
all the
random
neural nets did
labels.
well.
So
They basically
they
memorized the entire
wanted to
data
test
set,
out to
and
see
it
how
doesn't take
well
much. Where's
a
the
lot of this learning
there's the
theory
parameter size?
works.
It's not too big,
And what
and
they did
yet
is they
like
started abusing the
they did
data
one a neural net which is
and
just two
seeing
layers
how
deep,
well
and it
a
did all of
suite of standard
CFAR10
neural networks performed.
and things like
And
that. So it's like
what
there's
happens to the
basically bottom line. There's a
generalization
lot of
error.
capacity there, and obviously
And what
generalization
they
error
found is
was
that
not good,
for
or
training,
generalization was bad.
pretty well
They
all
abuse
the
it even
standard neural
further.
networks
Um, they also start randomizing the images themselves, and then they go so far as to basically just feed in random noise, just noise.
They randomized all the labels. This is on CFAR 10.
Okay. Yeah, I just got a request to listen on YouTube. If I'll try and listen on YouTube, but there may be an issue with feedback. Okay.
And it doesn't take much. Where's the there's the parameter size.
Okay, I'm going to mute YouTube right now because it's giving me lots of echo, and then I'll pop it back up when you let me know on Slack that there is a question, or maybe put it on Slack because it's yeah, it's just
bottom line. There's a lot of
okay. Well, anyways, I'll continue.
Generalization
Yeah.
was
All right.
not good, or generalization was bad.
Yeah, at the end, it's just noise, and it's still all of the
cells, and then they go so far
the architectures, whether it's CovNet or feed forward or whatever. What else did they use? They used like
request to listen on YouTube.
Inception, et cetera, et cetera. So some of the major ones, and they all just they memorized the noise. And then they did a fine tuning where they partially corrupt the data, and then slowly scale how badly they corrupt it. And it's just what you
pop it back up when
it's like a 1-to-1 ratio. As the data was corrupted, the generalization error proportionally increased. No surprise there. So they're showing that they go into it, things with like VC dimension and Rademacher complexity and something called uniform stability doesn't do the best job.
Architectures, whether it's CovNet or
doesn't do
feed forward or
the best job, doesn't fully explain the situation. And they also go into regularization,
so some of
the variety of regularization techniques, and the bottom line there is it helps, but no, it's not a miracle worker. It helps, but the help is small. So
it's just what you pop it back up when
they go into more theory and talk about a little bit and talk about what you can take home from this. And I think that's about as much as I can say here. Okay, I'll turn on the YouTube audio.
Uniform stability doesn't do the best job. Architectures, whether it's CovNet or doesn't do the best job, doesn't fully explain the situation. And they also go into regularization. So some of the
okay, I tried putting on YouTube audio, and I'm hearing what I said several seconds ago.
But no, it's not a miracle worker. It helps, but the help is small.
All I have is the headphones. That's it.
They go into more theory.
I have a headset with the microphone for it.
Take home from this.
Sorry?
And I think that's about as much as I can say here.
It's not possible. He has speakers on or something.
Okay, doesn't do the best job.
If you have questions, just
doesn't do.
if you have questions, maybe ask on the YouTube.
Fully explain this.
Okay.
They also go into regularization.
Next one.
Okay. I tried putting on YouTube audio, and I'm hearing what I said.
Is he on the call?
But no, it's not a miracle worker. It helps, but the help is small.
All I have is the headphones. That's it.
They go into more theory.
I have a headset with the microphone for it.
Take home from this.
Sorry?
And I think that's about as much as I can say here.
It's not possible. He has speakers on or something. Okay,
Doesn't do the best job.
if you have questions, just
Doesn't do.
if you have questions, maybe ask on the YouTube.
Okay.
They also go into regularization.
Next one.
Okay. I tried putting on YouTube audio, and I'm hearing what I said.
Is he on the call?
Okay, then. Yep. Thanks, folks.
I have a headset with the microphone for it.
Hello?
Sorry? I think that's about as much as I can see here.
It's not possible. He has speakers on or something. Okay.
Yeah, so
If you have questions, just if you have questions, maybe ask on the YouTube.
Okay. Okay.
Next one.
Yeah, okay. I tried putting on YouTube audio and I'm hearing what I said. So. Okay, then. Yep. Thanks, folks. All I have is the headphones, so that's it.
hello, can people hear me?
Headset with the microphone for it.
Hello?
Sorry? I think that's about as much as I can see here.
It's not possible. He has speakers on or something.
Yeah, so
If you have questions, just
thanks for the feedback. So I don't know why, but I can't hear anyone.
Okay.
But I would start off with the abstract of the paper that I wanted to present.
Okay, then.
So
Yep.
this is something that is very close to what I want to do in future. It's related to forecasting, but oftentimes we have seen that
Can people hear me?
the time series data that we deal with,
Hello?
they cannot be the data could not be approximated using stationary signals. Like, we cannot consider them as stationary, and we have to use those techniques that
Thanks
are
for the
more
feedback.
relevant to
So,
non-stationary
I
signals
don't know
and
why, but I
non-stationary
can't hear
data.
anyone.
So in
But
in the context of
I would
processing
start
and
off with
extracting features from
the abstract of the
non-stationary
paper that I
signals,
wanted to
of course, one
present.
technique
So
that
this is
we
something that
use
is
as
very close to what
people from the
I want
signal
to do
processing
in
background,
future.
we use
It's
wavelet
related to
transforms
forecasting,
instead of the
but
usual Fourier
oftentimes we have
transforms.
seen that
And this paper that I want to
the time series data
present
that we deal with
is
they
related to
cannot
wavelet
be
transforms.
the data could
That's
not
the
be
first thing.
approximated
And the
using
second thing that I
stationary
would like to mention
signals.
is that
Like, we cannot
wavelet
consider
transforms
them
in this
as
case has
stationary,
been used for
and we have to use
decomposition
techniques
of
that
the
are
time
more relevant
series,
to
and then it
non-stationary
has been
signals and
used for
non-stationary
feature
data.
extraction.
So
And then it goes on to we use something that is called as the cascade correlation algorithm, and together we call it as WCCNN. And what we try to do is that we try to do forecasting using this. So just give me a second. So what is the difference between, because this paper, like this technique has been used couple of times, but what is special about this paper is that on top of the the net transformation coupled with the artificial neural networks, they're also combining this model with principal component analysis, which is PCA. And they have in this paper um, they have included the classical methods of forecasting and compared it the technique of simply using WCCNN. And then on top of it, they have also compared it with the cascade correlation network that I was talking about. Finally, they are talking about um, the uh, the advantages of incorporating the principal component analysis. So I would like to present this paper and Yeah, and that's it, I think. Thank you for giving me this opportunity.
Okay, thank you, Ramya.
Albert couldn't be here today, but he sent in a video.
A graduate student super interested in machine learning and BCIs. Unfortunately, I wasn't able to make it today, so I pre-recorded a video. I'd like to talk about two papers today, which touch on using AI to bypass or fool human systems, work to mitigate these bad effects. For one, the paper Hacking Google reCAPTCHA v3 using reinforcement learning discusses using an RL model paired with divide and conquer to click the reCAPTCHA button. And it was able to achieve an accuracy of 96.7% on a 1000 by 1000 screen resolution. The reinforcement learning agent was used to beat the Google ML model, which worked to try to detect any irregular mouse movements to catch any bugs. The researchers implemented a grid along with the Markov Decision Processor (MPP) to guide the mouse to click the reCAPTCHA button without being detected by the Google model. Some proposed next steps would be to try the model on different pages and resolutions of screens. Another paper, which I'm sure most of you have heard about, is Defending Against Fake Neural News, which proposes the Grover algorithm, which is able to generate news articles extremely similar to that of humans. It was also discovered that the best models to generate fake news are also the best models to catch it. Indeed, the Grover discriminator model was able to detect fake news at an accuracy of 92%, compared to the previous 73% by state-of-the-art deep learning models. The Grover model was able to outperform OpenAI's GPT-2, both in metrics of perplexity and human ratings. However, the Grover model is very large, with over 1.5 billion parameters, and took around 2 weeks to train. Combining both a language model, which uses probability, along with distribution of different news elements, like the domain, the website, or the heading, it's able to take in all those conditions and generate a news article. Next steps include working with integrating actual knowledge and facts to actually catch the fake news, rather than just using the distribution. From reading these two papers, I realized that it's really important and thoughtful to discuss these ethics and social impacts of AI. From the Grover paper, it was discussed that they decided to release this model in order to help with the detection of fake news, even though malevolent people may decide to use it to generate their own fake news. News platforms like Twitter and Facebook, as well as article websites, must integrate these models into their systems and detection models. Google must come up with a capture model that maybe improve the rule-based algorithms, which is what I was discussing with the author of the paper. It's important to understand that though AI can be used for bad purposes, like hacking or generating fake news, it has the capability to mitigate these effects as well and work against them in making the world a better place. AI is truly a double-edged sword.
That's it, yeah.
Hi, my name is Owen. Okay. Hi, my name is Owen. So tonight I'm going to introduce this paper that I find it very interesting. This is related to action recognition, which is uh, a video-based recognition, right? So the title is a closer look at spatio-temporal convolutions for action recognition. So I've been following this author called Dutran, and we've been working also in some research related to gesture recognition. So 3D CNN, 2D CNN was part of things that I start learning. So that's why I came across this paper. So Dutran, and there is this Yang LeCun, the famous guy. So from Facebook. So this paper, the motivation is from the observation that 2D CNN, the two-dimensional convolution neural networks, applied to only individual frames of the video, and it's been remain a solid performer in action recognition, even it's only 2D. So it's just analyzing, they call it a bag of frames, right? It's not going into temporal dimension. So in this work, right, uh, they demonstrate the accuracy advantages of 3D CNNs over 2D CNNs within the framework of residual learning. So it's the ResNet. So and then furthermore, they also introduce uh, a new 3D CNN block. They call it block, not architecture per se. So it's a 3D CNN block, which they call it factorizing the filters into separate spatial and temporal components. And it yields gains significantly accuracy. So just a background, another background of this paper is that an image-based 2D CNN operating on individual frames of the videos of a video achieved performance remarkably close to the state of the art on video recognition. They use a sports 1M benchmark. So according to them, it's kind of surprising that 2D CNNs managed to, for action recognition, right? So it's surprising and frustrating according to them. So because 2D CNNs are unable to model temporal information and motion patterns. So how can they how can a 2D CNN manage to do this kind of task? So based on this result, we can postulate that the temporal reasoning is not essential for accurate action recognition, because 2D CNNs, analyzing frame by frame image managed to do it in 2D rather than 3D way. Then in this work, they challenge this view and revisit the temporal reasoning in action recognition by means of 3D CNNs and the network that performs 3D convolutions over the spatio-temporal video volume. So they introduced a new 3D CNN block that it was, I don't want to go into details, but it was, maybe I can show you a little bit here. Is it here? Okay. Yeah, it's too small, but anyway. Okay, so I also cited from other writings about this related to this paper. So currently, two-stream model. Two-stream model means you have two modality of images. One is RGB, the usual RGB, 3 channels, and the other one is optical flow. Optical flow, they call it handcrafted feature because it's not pure from images, right? Video. So this one, according to this paper, according to this writing, optical flow is slow, and also it's not a raw feature because it's handcrafted. So based on this proposed model, the new model, optical flow, generating optical flow is no longer really helping on video understanding, on video recognition, right? So this paper, they proposed this new 3D CNN block, they call it R2+1. So basically they how do you call it? They separate the spatial and temporal components. That's what they did. 2 and plus 1. So which operate the R2+1 kernel operates on 2D convolutional kernels on frame first, and then operates on 1D convolutional kernel for the temporal features. Oh, this is the picture actually. Right? So this is the 3D, and this is they separate into 2D.
Hold it into the camera.
There you go. Yep.
We'll present it later.
Okay. Hopefully, yeah. So that's it. I mean, yeah, a little bit closing. So according to this writing also, the video understanding is very popular research topic from recent active research from Facebook and Google. So there's another paper that is followed by this paper from Google, and they said that, yeah, we know the performance of action recognition is still far away from image classification. And according to him, we believe that there will be a new way of video classification, video understanding, as good as ResNet today.
Awesome. Okay, so I'm going to cover, well, I came across MIT News. The paper is called Structural Supervision Improves Learning of Non-Local Grammatical Dependencies. And in more simple terms, teaching language models grammar really does make them smarter. So basically, the article sums up the abstract very well. And what they're trying to do is that Siri and Alexa, these systems kind of are very sort of juvenile in how they function and how they work and how you interact with them. And what they're able to do is train these models, train a system to basically understand human grammar. And it gets very close to how we would understand human grammar. So basically what they're doing is they're using psycholinguistics to sort of peer into deep learning models to see how we as human beings understand grammar and interpret when things are incorrect. So Peng Chen and Ethan Wilcox are graduate students at MIT and Harvard University, and in a pair of papers we present in June, they, through Computational Linguistics Conference, through Harvard and University of California and IBM research, they find evidence that grammar-enriched deep learning models comprehend some fairly sophisticated rules, performing better than models trained on little to no grammar and using a fraction of the data. So grammar helps the model behave in more human-like ways. The sequential models don't seem to care if you finish a sentence with a non-grammatical phrase because they don't see hierarchy. So basically how they work is they use a recurrent neural network grammar model, which is LSTM. And what they do is, let's see here. They found that the best performing model, which is the RNNG, recurrent neural network grammar model, showed greater surprisal when exposed to grammatical anomalies. So for one example, it would, like one construction would be called a dependency between a filler and a gap in a sentence. So even when more complicated constructions of this type are shown to grammar-enriched models, they behave like native English speakers. They clearly know which ones are wrong. So, of course, we all know bad grammar sounds kind of weird when we hear it, and these models are able to interpret that with very little input. So, to conclude, basically, they plan to run their experiments on larger data sets to find out if grammar-enriched models learn new words and phrases faster. So, just as submitting neural networks to psychology tests is helping AI engineers understand and improve language models, psychologists hope to use this information to build better models of the human brain. And some component of genetic endowment gives us the rich ability to speak. And so they are sorts of methods that can produce insights into how we learn and understand language when our closest kin can. Specifically.
So, hey everybody. So just to start off, I think it's a very... Hi everybody, I'm Florian. I'm a data scientist at BMO. And I'm here to talk a bit about privacy and machine learning. And I think it's a very important subject which is greatly overlooked by a majority of people. Just to start it off a little bit. So I have a little bit of questions. I can safely assume pretty much every one of you has a LinkedIn account, right? So here's my question. If you publish an article on LinkedIn, who owns the article? You or LinkedIn? Have you ever thought about this when publishing on LinkedIn? Who owns the data of LinkedIn, right? So we all have multiple social media accounts or a Gmail account. So which of you have read the privacy regulations and rules and statement for the business? Pretty much very few people do it, right? As an idea how important all this privacy data is, so think how Google or the Google business evolved. So Google started off with a search engine, right? And they quickly reached a limit what they can do with just simple people search data. So they started doing Gmail. And Gmail, they can understand, okay, get a bit of context of what the person from the person and what people are talking about, and then they're gonna go to Google and search something, right? They're gonna get an email and then gonna go to Google and search something, and then they understand what's happening here. And then what was the next step, right? Was Google Maps. So now all these services were just integrated to collect more data on users to better sell them advertising. So there is a lot of value in this kind of private data. And especially recently, last year or last 2 years, more and more people were talking about this and thinking about solution of this. And one of this is like OpenMind. And this is one of the first papers from OpenMind. And what they had created was a general framework for privacy-preserving machine learning. And the idea is to have like some kind of federated learning. So the idea is that you no longer do the learning yourself. So every person is owned in a network, and every person has its own data, and you send the neural network you want to learn to the network, and then the person learns the neural network on his machine, and then sends you the improved gradient back to you, right? And then you get your gradients from all the data from each individual person, and then you aggregate it and you optimize your neural network. And there are a lot of difficulties with this involved. A lot of difficulties. Like one big part of the paper, they just describe how they did it from a programming point of view. So they write some bit of like higher level wrapper architecture, which says, okay, this is like kind of a tensor. And if you say you want to do addition, or you want to do multiply or max, you tell it, do this. We just say, okay, do this. It's just an description of doing it, right? A computation graph. And then when you get this tensor, this kind of abstract tensor, it just calls the native library. In this way, it calls the native PyTorch library if you're running PyTorch. So they talk a little bit about dealing with all these troubles. And let's say what this graph contains is basically an empty tensor, which you initialize yourself. This helps you to prevent malicious attacks. So one way is like you write the tensor, which just copy paste your data, right? And then you get sent it back the gradient for the tensor, right? So you have to initialize the tensor yourself. And then they say, how do you federate it? So basically you run it on your network, you initialize the tensor to architecture, and then you send the architecture to every person in that network. And then every person in that network does the computation on his own device and sends you back the gradient. But there is another trick they do. they do add some noise on the gradient to make it more privacy preserving. And they show they can achieve very high level of privacy preserving for just losing maybe 10% of performance. And another issue is that, so right now they have lots of problems. It's just a very beginning. And the other problem is it's based on the trust on the worker. So each individual person just don't send you back random noisy gradients, right? So you kind of trust the person. And they run two data sets. One was Oxford, like, let me see. Second. One was basically on rents, and one was on a diabetes data set. And especially a central application for this is if you want to work on medical data. Whoever had some surgery or had some examination done and opted in to have their medical records shared for research. And whoever followed up what happens in that process, right? And for one point, there was the 1,000 genome project, and there were certain genomes that could reconstruct family trees from it and then trace it back to a single person. So it's not as randomized and anonymized as much as you imagine it is. But let's turn it back and say, okay, every person has its own genome on its phone and you want to help research, then they can train the tensor on your phone and you just send it back and they never looked at your DNA. So when you send it to the worker, you say, okay, this is the tensor I want to train and this is the location of the data. And most of the time, the worker owns the data. But it's a more general framework, so not necessarily the worker needs to own the data. And another big problem they have right now is like much slower. Like if you run it natively in PyTorch, for the example, it takes like 2,200 milliseconds, 220 milliseconds. But if you run it in their framework, it can take 10 seconds. So it's much slower. But I think it's the right direction to go, and it allows you to also more democratize kind of AI and machine learning, right? So a lot of problems like having bias in data sets or having kind of no input on your data. And if you say, okay, every person can add with its own data or can add or contribute to it, you kind of democratize it, right? Anyway.
Cool. Awesome.
Good.
Stay in the center of your square.
Okay. So the piece. Wait, what?
Introduce yourself.
Sure. So hello everyone. My name is Owen Ho. I'm a data scientist at LBC, and I'm currently doing my master's at Python in recommender systems. And the reason why I chose this paper, which was published, I think, probably late September 2018, was two things. The first thing is, from a recommender system perspective, generally speaking, most of the customers that deal with recommender systems, they think that recommender systems are there only to benefit whoever is building it. For example, if it's Amazon, they just want to make money out of the customers. If it's Google, they want to do something, to collect data. But it loses the point where a lot of information needs to be passed on to the customer to be able to trust the recommender system. And this was the whole point of this paper is to make sure that there is a reasoning behind recommending a specific product to each customer. So for example, if the customer or the client trusts the website, they trust the recommender system, this means that they can believe or they can have that feeling that this is actually a personalized product for this specific customer, and instead of thinking or having that that thought that if the company is being basically trying to push that specific product to me. So Microsoft Asia did this paper where they are trying to use reinforcement learning, put it to any recommender system, and it generates a reasoning behind having a specific recommendation. So, for example, Amazon right now, what they have is if you bought this item, you also you would probably buy X or probably buy Y. This is one of the reasonings that this system can get. And instead of having it prior to recommendation, what they're trying to do, given any recommender system, basically they have two kind of reinforcement learning models. Both these agents, what they try to do is they try to something like attention-based, where they try to predict what is the next item, and the other agent tries to understand what is the correlation between the two items. So for example, given a session, item 1 and then item 2, one of the agents tries to predict what is the probability that it's going to be item 3 given these two items, and then the other agent tries to understand the correlation between the item 3 and item 1 and 2. The reason why I think this paper is very interesting, other than it actually builds trust, and ethical AI is getting really a lot of attention recently. It tries to kind of get into that field. Other than that, is you can get tons and tons of information about the recommendation accuracy from something like that. What I mean by that is the way they're testing this model is actually by having 4 data scientists and marketing research people, where they sit and they try to understand what is the correlations, and they test the model based on those 4 people. What I mean is, I personally, I think I know the product. I try to understand the correlation between product 3 and product 2, and I test it against my model. In my opinion, this is a really naive way of testing a model, but this is the first time they're actually trying to do something like this. No one apparently yet has tried it. And like, for example, in one of the projects that I'm working on, is actually, this was the main, the people tried recommending this, trying building this with a reason code. If there was no reason code, they don't want to recommend a system. The reason being is, with no reason code, the client doesn't believe that you're actually trying to have a personalized recommendation. Therefore, they're not taking your recommendation seriously. The limitations with that is, other than definitely having 4 people trying to find the reason code, and you're training it based on actual 4 people's comments, the second problem is extremely slow, because for the next item recommendation, you're running the normal model, which is assuming that you're running already like the normal recommender system model, which assuming it's just collaborative filtering. You're running one reinforcement model, and then in addition to that, running another reinforcement learning model to be able to get the correlations and to be able to get the reasons code. And complexity-wise, I think it's very, very complex. And the reason being is, for example, the very basic and easiest approach to having a recommender system is, okay, let's put in a collaborative filtering. Let's put it in a rating matrix and do an FVD on this, where FVD basically breaks down this whole big rating matrix of user and items ratings matrix into much too smaller matrices that you can use and manipulate easier. But we have no idea how that these breaking down happen. We just have some embedding for the user, some embedding for the items, and that's all what we have. So getting that explainability up until this point was almost impossible. If we go even a bit more technical, and let's say we're building a deep learning model, I don't think there is a possible way to get that reasoning code. That's why I think this paper is very good in its field, and I believe it's one of the most interesting papers I've read recently. So that's it. Thank you.
Hi everyone, my name is Yuri. I'm happy to presenting today. I'm an aspiring data scientist currently looking for a position, and today I will be presenting you about deep reinforcement learning based recommendation with explicit user item interaction model. And as you can see, there has been already like 2 previous people in this group presenting a paper regarding reinforcement learning, and which I will collaborate on that. I'm kind of very lucky to proceed after Omar, because he obviously had some very related work with me. The reason why I have chosen this paper is because, honestly, because of Omar. We will be working on some recommendation system. He will be he's my mentor and will be teaching me more from the field. And also I found it quite exciting, which the reason why it's exciting is that incorporating reinforcement learning into recommendation system is something new, and we agreed with Omar that it's going to soon be hype. So obviously we all know, for example, Netflix. The more the luckier ones even watch Netflix if they have time. And there is one problem with a lot of items, right? You experience difficulties to choose the best ones to actually you want to maximize your utility, and this is the reason why recommendation systems come into place, because it helps you to choose the movie or item of the greatest interest. Previously, and in paper, the guys call it state-of-the-art models. They use even logistic regression, matrix factorization, collaborative filtering, and other methods. But the greatest value of this paper is in the fact that the techniques I named, they lack, they don't address two facts. So for example, they only consider users preferences as static, which is we kind of know it's for example with age, like your preferences do change, which is one limitation of these methods. Other limitation is the state-of-the-art methods focus on immediate feedback of the recommendation system rather than long-term reward, which is again the reason why reinforcement learning comes into place. The guys in this paper addressed these problems because they state that it's very likely that users' preferences are dynamic. And their suggestion is basically to model a sequential decision-making process, which would help recommendation system to understand the user and increase the long-term rewards. And they emphasize in this paper was to examine what happens if user U consequently experience satisfied or unsatisfied recommendations. To address the second issue, they really wanted to maximize your utility with being exposed to long-term benefits. So they proposed a solution, and now I will try to elaborate with some use case. So imagine that you have a recommendation system which recommends you an item, but you are not very satisfied with that item. So in other words, the recommendation system was wrong. So what the previous or the state-of-the-art systems used to do, they try to again analyze and recommend you other item in next process. But with that model, they in short call it DRR. The DRR model takes a step back, and rather than risking and suggesting you other item, it goes step back and recommends you item from the safest area. So for example, let's say that previously you watched you've seen a movie Terminator, and the next movie was High School Musical, right? And you didn't like it. So in the previous cases, you would the recommendation system would examine and recommend you other item. But with reinforcement learning, taking the step back, the system probably or the system knows that Terminator, which has been liked you, the safest area is probably some other action movie like Rambo or whatever. So they developed the solution in this paper, and this is the reason why I really like the paper, because the paper proposes the design of such model, and they basically model recommendation, reinforcement learning, or they utilize reinforcement learning based recommendation techniques for large-scale scenarios, and carefully models and explicit interactions between user and items. They built on their assumption that modeling the future interactions between user and item can actually boost the whole performance, which in the conclusion of the paper they proved it was correct assumption. I also like the way how they evaluated that model, and because you can evaluate in two ways. So first of all, offline, which is a safe safe way to evaluate, and the other way is online, which can be very costly and difficult. But they did that because they came with a solution called online evaluation with environment simulator. So in conclusion, the guys came to the results that DRR's recommendation system as a sequential decision-making process adopts an actor critique scheme, and it takes into consideration both immediate and long-term rewards. And they also proved in that paper on real-world data sets that the superiority of this model over the state-of-art models is really important, and the performance was much more was better. So thanks for the attention.
Hi everyone, my name is George Lopez. I'm an author for TDS for now, and I would like to present the paper Predicting Crime Using Twitter and Kernel Density Estimation. I chose this paper because it makes society better. It's a worldwide application of machine learning. So crime prediction is used by anti-crime organizations for optimizing the scheduling of their limited resources for patrolling in hot crime spots. This prediction has been enhanced by using Twitter messages processed with the NLP machine learning technique known as latent delay allocation, or LDA. So basically, LDA, what it's going to do is to uncover the hidden topics in that pervades a large text corpus. In this case, the text corpus is the Twitter messages. So the intuition is that the Twitter messages contain the place where the person is tweeting. For instance, if somebody is in the airport, is going to tweet something like American luggage airplane, so that gives us a clue that that person is in the airport. So how are tweets used to make the prediction more accurate? It uses KDE, that is kernel density estimation. It's a technique used to discover the PDF of a distribution. So usually we have a uniform distribution that is like an histogram, and we would like to know what is the shape of that distribution, and we can use KDE in order to find out what the distribution looks like. So LDA works by providing a hyperparameter, that is the number of topics that we would like to extract from the text corpus. And usually this parameter is K. And well, there's many techniques for determining this K number. So the higher the K is, the higher the granularity that we are going to extract from the text corpus. So, for instance, let's say that we have a crime that is, let's say, is prostitution. So, when we apply the LDA algorithm, it's going to, and we extract 500 topics. Let's say that the higher probability topic is given by the words lounge, studios, continental, village, Ukrainian. So that might be an indication that where the crime is being committed. In its study, Gerber, who is the author of this paper, analyzed the city of Chicago, Illinois, in the US, and what he did was to divide Chicago in like this.
We'll go through the details later. Just wrap up maybe.
Okay. So he analyzes each of these cells and determines what possible crime is being committed in that area by applying the LDA algorithm plus the tweets that are being taken place in those areas. So he claims having achieved a higher accuracy in the prediction of crimes. Basically, what I did, that I'm not going to enter into details, but basically, for most of the crimes, he has found an improvement in the prediction, and for the others, he found that the prediction is not that good. Many crimes, such as homicide, weapons, and so on, they don't have a very high prediction accuracy. So, in my opinion, this paper presents a good effort for improving crime prediction that is based solely on KDE by adding Twitter analysis using LDA. However, the gains in prediction accuracy that the author claims do not extend to every crime type, as I have mentioned. So maybe other features may be used in order to enhance the prediction of crime, such as the weather. So I've seen that there is another paper that involves the Twitter sentiment analysis and weather in order to improve the prediction accuracy of the crime prediction. Thank you.
Awesome.